Welcome to this talk about our work on the 3D hash join. My name is Daniel Flachs and I'm a PhD student at the University of Mannheim. In the next couple of minutes, I'm going to present to you the key aspects of our work. Let's start by defining the problem. Joins are central operations in database systems, and evaluating them efficiently is therefore of great importance. One prominent way to evaluate an equijoin is based on hashing, which consists of two phases, build and probe. Our work focuses on hash tables that resolve hash collisions by chaining. This means that each hash table bucket contains a linked list of entries hashing to the same bucket. A standard chaining hash table maintains one collision chain node per inserted key value pair. In the context of joins, a key is a join attribute value, and a value is typically a tuple pointer or a tuple identifier. Usually, it is assumed that collision chains remain comparably short if the hash function is good. However, this assumption only holds if there are no duplicate build keys. If there are duplicates on the build side, collision chains grow proportionally to the frequency of the respective keys, like in the figure on the right. During the probe phase, this causes a large number of main memory accesses and join predicate evaluations when traversing the collision chains. Moreover, collision chains must always be traversed until the end, because the search can just be terminated after the first match. Duplicate build keys occur if the hash table is built on the foreign key side of a key-foreign key join, and are even completely unavoidable in case of many-to-many joins where neither side is unique. In order to address duplicate build keys, we propose the 3D hash join with its underlying data structure, the 3D hash table. The 3D hash table works like a standard chaining hash table, only that it groups entries with the same key together, using two different node types. Instead of maintaining one collision chain node for each inserted key value pair, we maintain one main collision chain node for each distinct key. Main nodes store keys and values, while subnodes only store values. 3D refers to the three-dimensional organization of the hash table, which consists of a hash directory, main collision chains, and subchains beneath the main collision chain nodes. When a key is inserted for the first time, a main node is created for it, but whenever another pair with the same key is inserted, we put the respective value in a subnode. This subnode is stored in a subchain branching off from the main node. When inserting a key value pair, we must first perform a lookup of the key to see if it's already present. Therefore, the complexity of the insert operation is linear in the length of the main collision chain instead of constant as for the standard chaining hash table. To look up a given key, we must first determine the respective hash table bucket and then traverse the main collision chain until we either find the key or there are no more main nodes to examine. If the key is found, we can terminate the search right away, because another main node with the same key can't exist. We then return a pointer to the main collision chain node where the key is stored. Note that all values in the subchain beneath the respective main node belong to the searched key and are therefore matches. Now let's see how the 3D hash join can be used to compute the join between two relations R and S on some equality join predicate P. We denote the standard hash join using a chaining hash table by Hj, and our approach by 3D. In this example, we first build a hash table on relation S and then probe it with tuples from relation R. The main difference between the standard hash join and the 3D hash join is its output. The standard hash join returns tuples from R and S that match under the predicate P, whereas the 3D hash join returns nested tuples that contain a tuple from R and a list of matching tuples from S, at least conceptually. In reality, capital S is a pointer to a main collision chain node in the 3D hash table. We call this packed search result a nested tuple, and we arrive at the final result by unpacking it using an operation we call unnesting. Note that the 3D hash join produces at most one output tuple per probe tuple. The Unnest operation is the last building block to compute the final join result. It's fairly straightforward and expands each nested tuple's right-hand side capital S and combines it with the left-hand side R to produce the final result tuple. The reason why join and unnest are two separate operations is that this allows for deferred unnesting. Nested tuples do not have to be unnested right away, so not immediately after the respective join. Instead, this can be delayed until after a second join, for instance, which can increase performance. This is due to the fact that the second join only has to process fewer nested tuples instead of potentially many plain result tuples. Also, the second join might eliminate some nested tuples that won't require an unnesting later on. For deferred unnesting to be applicable, the join predicate of the second join must not refer to the nested part, but only to attributes from the probe side of the first join. In the example shown here, this is the case. More generally speaking, regarding plan generation, a possible heuristic would be to move the Unnest operator upwards in the operator tree until beneath another algebraic operator that requires attributes from the nested part capital S of a tuple. In practice, the exact selection and placement of join and unnest operators can, for instance, be decided by a cost-based query optimizer. We conducted an experimental evaluation for which we implemented and compared the standard hash join and our 3D hash join. We measured the runtime of both join implementations in different experimental setups. A single key foreign key join, a single many-to-many join, and another experiment with 2 joins to demonstrate the effect of deferred unnesting. As a relative performance measure, we used the symmetric relative difference of the join execution times. It is a signed measure where a positive number means that the 3D hash join is faster, and a negative number indicates that the standard hash join performs better. Note that an SRD value of x means a slowdown or speedup factor of the absolute value of x plus 1. In the first experiment, we measured the runtime of different execution plans for a single key foreign key join between a key relation R and a foreign key relation S on integer attributes. We varied the cardinalities of both relations between about 1,000 and 33 million tuples. The foreign keys were generated uniformly or with skew according to a standard ZIF distribution. Also, we varied the number of duplicate foreign keys using a parameter called T. The higher T, the more duplicates in the foreign key column. A more detailed description of the data generation can be found in the paper. We evaluated 4 plans in total, each of the 2 possible join orders with both join implementations. We then compared the best plan from the standard hash join to the best plan from the 3D hash join and computed their symmetric relative difference. We ran the experiment for a large number of parameter combinations to cover a large fraction of the different possibilities that can occur in practice. The figure shows a heat map of the performance measure for different parameter combinations. In each of the 4 subplots, the cardinalities of R and S are on the X and Y axis respectively. The left column shows the results for uniformly distributed foreign keys, the right for a skewed foreign key distribution. The number of duplicates increases from the upper 2 to the bottom 2 subplots. The 3D hash join outperforms the standard hash join if the foreign key side is smaller than the key side, especially in the presence of skew and a large number of duplicates. For the second experiment, we considered a many-to-many join between 2 relations R and S. The hash table is built on the smaller relation S. In the table, you can see an excerpt of our measurements. It shows that the advantage of the 3D hash join increases for larger cardinalities and larger number of duplicates. Overall parameter combinations, we observed that the 3D hash join is never slower than the standard hash join. The last 4 columns in the table show the average and maximum collision chain length for both approaches. As one can expect, collision chains become longer in the chaining hash table when the number of duplicates increases. In contrast, the 3D hash table maintains a constant main collision chain length. With the third experiment, we wanted to demonstrate that deferred unnesting can be beneficial. There is 1 key relation R and 2 foreign key relations S and T on which the hash tables are built. S and T contain the duplicates. The join graph has the shape of an inverted star. This shape can, for instance, be found in query number 13 from the join order benchmark. We compared the 2 query execution plans shown on the slide. The left plan uses 2 standard hash joins, whereas in the plan on the right-hand side, unnesting is not performed immediately after each join, but deferred until the end of query execution. For the experiment, we generated data in the relations such that the overall join between all three relations is very selective, while each single join between R and S and R and T is not. The table shows some of our results. The first column contains the frequency of each foreign key in S and T. The last three columns show the symmetric relative difference between both implementations for the total runtime as well as for build and probe separately. It can be observed that with an increasing number of duplicates on the build side, the 3D hash join performs worse in the build phase, but can make up for that in the probe phase. To conclude, we proposed a novel hash table organization that is simple but also powerful in case of duplicate build keys. Higher build costs can pay off if fewer main memory accesses and predicate evaluations are necessary during the probe phase, especially in the presence of duplicates due to data skew. As an additional technique, we introduced deferred unnesting. The 3D hash join produces nested tuples that need to be unnested to get the final result. This unnesting step does not have to happen immediately after the respective join, but can be delayed until attributes from the nested part of a tuple are required by another algebraic operator. This can improve performance. And with that, I'm at the end of my talk, and I thank you for your attention.